Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the real analysis class. In today's lecture, we will discuss an important topic from real analysis written by Walter Rudin. That is the difference between field and ordered field. So, in the short lecture, we will discuss the two important definitions that we will use in incoming lectures. What is the difference between field and the ordered field? Uh, the concept of ordered field is actually related in some way uh, by the with the ordered sets that I have discussed in my previous lectures. So to understand about ordered field, I recommend that you firstly watch my previous lectures that based on ordered sets. So let us discuss what is the field. A field and the ordered field both are actually name of a set. Firstly, field is not a function, not a mapping. These are the name of set. This is first thing. So firstly, how we can define field? Let F be a non-empty set. This is the first condition. Suppose F is a non-empty set with two binary operation, with two binary operations, let us say the binary operations are plus and multiplication, defined on F. Suppose F is a non-empty set, there are the two binary operations plus and multiplication that are defined on the elements of F. Then F is called field if it satisfies the following 11 properties. First, F plus is an abelian group. The second one, the non-zero element of F, that can be written as F minus 0 under multiplication is also an abelian group. The third one, distributive laws hold. So if a non-empty set F that satisfies these 11 properties, then that such set F is called a field. The first, F should be an abelian group. When we say F is an abelian group, it will satisfy 5 properties. First is closure property, second is associative property, third is the identity element, fourth is the inverse element, and the fifth one is the commutative property. So 5 properties are covered here. In the similar way, when we say the non-zero element of F, that is F minus 0, this should be also an abelian group under multiplication. This will again satisfy the 5 properties. So there are the total properties are complete here. Lastly, the last property is the distributive law. The distributive law are of two types. One is left distributive law and second is right distributive law. Left distributive law of multiplication over addition can be defined as if A, B, C are any 3 elements of the set F, then A into B plus C equal to A into B plus A into C. This is the left distributive law because here we multiply A from the right side. For the right distributive law, uh, we multiply A from right side, that is equal to B dot A plus C dot A. So a set F that satisfied these 11 properties is called a field. There are thousands of examples available for field, but it is not our purpose to study about field in detail, because this is the class of real analysis, and field, group theory, rings, etc. are the topics of abstract algebra. Uh, so only over the numbers, there are only three fields that will be under discussion. One is Q, set of rational number. Set of rational number. This is the one of the important field over the number. The second one is real number. Set of real number are set of real number. And the third one is C, set of complex numbers. Set of complex numbers. So over the numbers, we will discuss only these three sets that form the field, that fulfill all these 11 properties. Next, now we discuss what is the ordered field. How we will define ordered field. Ordered field. For ordered field, a set F firstly should be a field. So if you read the pages of mathematical analysis written by Walter Rudin, the Walter Rudin says that a field F that is also an ordered set. A field F that also fulfill the condition of ordered set is called ordered field. A field F that also fulfill the condition of ordered set is called ordered field. We can alternatively define ordered field like as this. A field F that satisfies order axioms, also called properties of inequalities. Properties of inequalities. So this definition is actually give the same concept as the definition available in the book of Walter Rudin. This is a simple, very simple definition. A field that satisfies the order axioms is called ordered field. Now, what is the ordered axiom, or what are the properties of inequalities? In the properties of inequalities or the properties of order axiom, the first property you know very well, trichotomy property. In trichotomy property, we say that for all xy belong to F, F is any field. It may be Q or C, or it may be other than these three. For all xy belong to F, either one of the following property can be satisfied. Either x is greater than y, or x is less than y, or x is equal to y. This is the trichotomy property. The second one is transitive property. Transitive property says that for all x, y, z, if x, y, z are the three elements of the field F, then if x is greater than y and y is greater than z, this implies the first number x is greater than z. Actually, if you notice, these two properties are actually the properties of the for any ordered set. A non-empty set is called an ordered set if an order can be defined on that set. And when we define an order on uh, that set should satisfy these two properties. One is dichotomy and other is transitive property. Next, in the properties of order axioms, the third property is third property is transitive additive property. Additive property says that if x, y, z are the three elements of a field f, and if x is less than y, then by adding z on both sides of the inequality will not change. That is, x plus z is less than y plus z. The last one is, this inequality can also be written as if x is greater than y. That have the same meaning. Then x plus z will be greater than y plus z. Last is the multiplicative property. Multiplicative property. Multiplicative property says that if x and y are the two positive elements of the field f, then their product will also positive. That is, if x and y are the two positive elements of the field f, then their product x and y will be greater than. So a field f that satisfied all these four axioms, that are actually the axioms of the properties of the inequalities, is called the ordered field. Now there are, at this time we have three fields. We can check that which of the following field is not an ordered field. Obviously you are absolutely right. The set of complex number C is not an ordered field. Because why the complex number C is not an ordered field? Complex number C is not an ordered field. Why? Because we cannot define an order on complex number. Actually, if you observe, uh, what does represent the properties of inequalities, or what does represent the order axioms? Actually, the order axioms represent the comparison between elements of the field f. You say for any two elements x and y of f, either they are equal or they are not equal. Either one is bigger than the second, or one is less than the second. So this represents the comparison between the elements of the field f. Now, in complex number, you can you know that you cannot compare any two elements. For example, if you have first complex number z1 is equal to 3 plus 8 iota, and the second number is z2 is equal to 8 plus 3 plus iota. Can you say that z1 is bigger than z2? Can you say that z1 is equal to z2? Can you say that z1 is less than z2? You cannot say anything among these three. So that's why you cannot compare any two elements of a complex number. This shows that the complex number, that is actually the field, is not an ordered field. We cannot define an order on complex number. So there are the only two fields remaining that are actually the ordered field. One is rational and the other is the set of real numbers. Both of them are the ordered field. So this is the short and simple lecture about field and ordered field. I hope you completely understand this lecture. In the next lecture, we will discuss about complete ordered field. That is the very important topic of the real analysis. And in that lecture, we will discuss that the set of rational number that is actually ordered field, but not a complete ordered field. So we meet again in the next lecture. Take care. Allah Hafiz.